Volume happens in a 3D figure, and we could think about like a gift box, but when we look at a box, that doesn't really help us from the standpoint of calculus. So we could have a box, we could have a pyramid, and we could find the volume of all of these things. But we want to talk about shapes where you can't find the volume just from a standard formula. You have a right circular cylinder, and the volume here is 2 pi r squared h. So these are the things that we can do normally. What we're going to do is we find that volume is found by integrating the area. So to find the area under the curve, we integrate a function, but we are given that volume equals the integral from a to b of the area of x dx. And the important part to remember here is that when you're looking at a of x, it's because you're taking a piece of it, of cross section slicing perpendicular to your x-axis because we're finding the area with respect to x. We're taking a cross section with respect to the x-axis. Now, the smaller we make these cross sections, the better it is. Remember when we started off with finding the area under the curve by dividing it into pieces and adding those areas together? And the smaller we made those pieces, let me get another writing utensil. The smaller we made these pieces, the better the area became because we got smaller pieces. Well, the same thing applies here to volume. So the method we're looking at today is called the disk method. So if we were to divide this is the sphere, and we know that the volume of a sphere is 4/3 pi r cubed. So since the volume of a sphere is 4/3 pi r cubed, if we let r equal 1, this means this volume is 4/3 pi. And and that's a little bit more than 4. You can look up that decimal on your calculator. But notice that when we only have 5 disks, these are big chunky disks, and there's a lot of space happening in here between the sphere and the disks that we have chosen. And the more disks we get, the smaller this error becomes in here, and the closer we can become. So you can kind of see that this one's really close. And if you look at the decimals, when you use 20 disks, you get a better approximation. Now, what we're going to find from here is we called volume to be the area, the integral of the area. So the disk method is going to say that volume is equal to the integral from a to b of pi r squared dr, whatever r is. And we're going to make a note here that r, our radius, r equals the radius of the function. And we're going to add to that note that r is perpendicular to the axis we're rotating around. We can call it the axis of rotation. It is not always the axis, so it may be better to call it the line of rotation because r is always perpendicular to the line of rotation. So there's a big conversation about the disk method, and uh, there comes a point where there's part of it missing. I just called all the disk method. No one's going to ask you these words, so it's all okay. Let's look at a specific example. The way these problems work is we're going to be finding volumes. So we're going to take some some curve that we have. Let's call it f of x like this, my nice random f of x. And we're going to take this f of x from a to b. And what we're going to do is we're going to rotate this around the x-axis or the y-axis. This one we're going to rotate around the x-axis. Now this is where my art skills kind of fail me, but here's f of x down here. So what we have is we have a 3D figure that looks about like this. And it's a little hard to see, but it'll make more sense when we can pull in some 3D figures. Desmos does graph in 3D, so that could help you see it a little bit better. Not this one because it's very general. And be prepared that you can't use Desmos on your test. Now remember, our note is that we're using the disk method. So what we're doing is we're taking a random disk in the middle here, any random disk. We're going to call it this one. It's a little dark, but you can see the disc. Let me try that with a different color. I'm going to put this bright green on it maybe. And then you can see how this one goes around the back. That's how we generally indicate that we're coming around the back. So we're taking this disc and we're taking a whole bunch of the discs, but because we're integrating, they're very thin and we're going to add them all together at the end. So because we're in the disk method, we're going to say the volume equals the integral from a to b pi r squared dr. Now remember pi is a constant, so we're often going to move it out front. So on this problem, we would say volume equals pi, the integral from a to b. Now this radius right here is always perpendicular to the axis we're rotating around. See how we're rotating around the x-axis? So this is our radius, and our radius is going to be equal to the equation for f of x. Right here in green in the middle, that's our radius. If we were to move, let me pick a different color that'll help me out. If we were to move over, our radius would be here, that the whatever the height, whatever the y value is in f of x, our radius would be here, our radius would be here, so it adds all of those up. So our radius then is f of x quantity squared with respect to x. Your radius will be the function if you're rotating around the x-axis or the y-axis. So while we're talking about the y-axis, let's see what that would look like. Let's move this a little bit. So let's say we have a graph that looks like this, and we're going to rotate it around the y-axis. So it's going to mirror out here, and it's going to rotate like this. So you would find that here would be your radius, and you would look at x equals a function in terms of y. That might blow your mind, but we're going to do it. So then x equals f of y. So we would say our volume then would be pi times the integral from a to b. And we're going to take whatever that function in terms of y is and square it with respect to y. Now our a and b, I didn't label those here sadly. So we have a, and we would go all the way up to whatever it tells us to for b. So before we get started with this problem, you always want to start with the graph. Your radius is going to be perpendicular to the line of rotation, in this case, the axis. So it's going to be important that you look at a graph so you can look at what's going on. So let's look at this problem. It says find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals the square root of x. So that's important here, from 0 to 1. So let's look at this graph. Y equals the square root of x is a graph square root that looks like this. And we're going to look at the volume from 0 to 1. Now what's important here is we're rotating around the x-axis. Now we're rotating around the x-axis, and if you look at our equation, it is in terms of x. That is what drives our disk method. I'm going to write disk method here. It is not the only method we're learning, so if you'll build this habit, it will help you later. And then in disk method, we have pi r squared. So what we're going to do is we're going to look at this graph. What happens is I'm not going to draw it in 3D. I'm going to come back to the 3D. But if you do the problem and label it well, it shouldn't be too difficult. So this is my radius right here because I'm rotating around the x-axis. This radius comes down and touches the x-axis. Now we should have labeled our graph y equals the square root of x. So then our radius is going to be the square root of x. So remember that in the disk method, we use pi r squared. So we're going to say volume equals pi, the integral from a to b, which is, let's go ahead and write that formula, a to b, radius squared dr. So we're going to say pi, the integral from a to b of 0 to 1. The radius is the square root of x, and we're going to square that with respect to x. Now this isn't a very difficult integral. Pi, the integral from 0 to 1. The square root of x squared is x dx. So we're going to bring down the pi. When we integrate x, we get 1/2 x squared from 0 to 1. So we're going to say pi. I'm going to move that 1/2 out here underneath pi. And then I have 1 squared is 1, minus 0 squared is 0. So my answer is pi over 2. Now that is the area, that is the volume formed when we rotate this around the axis. Now you could kind of see the 3D if we rotate this around the axis. You could see it coming down like this, and it kind of makes this shape. I have a really pretty version of that for you. So let me bring that in real quick. So on the left, you can see the picture with, they marked here the cylinder where we're going to slice to get the disc. And on the one on the right, you can see the figure in 3D. And there they have the disc, the one disc they pulled out for you. It has a little bit of width so that you could see why we have a dx for a delta x. All right, let's look at another one. So this one says find the volume of the solid obtained by rotating the region bounded by y equals x to the third, y equals 8, and x equals 0 about the y-axis. Notice that we're going about the y-axis. I did not mean to move that over. I apologize for that. So what we're going to draw here is we have y equals x to the third. So it looks like this. I call it the tall graph, y equals x to the third. We also have y equals 8. It goes across here, y equals 8. And we have uh, x equals 0. X equals 0 is our third line like this. The question is, which part do we shade? Like, do we shade underneath here? And if I scribble that out, you won't see it again, so I'm going to put an X on it. That is incorrect. You need to shade on the part that touches all of the lines you were given, all of the curves. You're given this curve and this curve and this curve. So when you look at these three curves, this part right here in the middle of it is your shaded area. That's what you're going to rotate around the axis. And we're rotating around the y-axis. I'm going to put this down here. We're going to rotate around the y-axis. So that means we need everything to be in terms of y because we're rotating around the y-axis, and that will be the disk method, which is pi r squared. So that means my radius is going to be perpendicular to the y-axis. Now, in Calc 2, in these problems, everything they give you, you're going to use. If you didn't use part of it, you made a mistake. So notice here that we have r equals, but we need it to be in terms of y. See the dy down here? That means we need to solve this for x equals, so x equals the cube root of y, or y to the 1/3. Both forms are good for now, but you know that when you integrate, you need the power. So I'm going to say r equals y to the 1/3. Now the question is, what do we do with this green line? Well, when we're in terms of y, that's a bound. And down here we have a bound. The x equals 0 cuts us off at the x-axis. The reason that that's important because that means the part in the third quadrant is not necessary because it draws that boundary there. And when we rotate around the y-axis, we end up with some figure that looks like this. You can't rotate on top of the graph. So if you're rotating on top of itself, then you've made a mistake. For example, my yellow shading on the left should not touch my blue shading on the right. It can't overlap. So now I have all this craziness here, and I'd like to erase it, but if I do, you won't get to see it. So, okay, so I cleaned it up here on the right. This is really what I'm looking for on the right, is all of these things written in here. Let me finish my disk and my pi r squared. So this graph right here is more of what I'm looking for on your paper. It'll help you determine what you need. And I didn't want to leave the screen because I wanted to be able to come back to it if we need. Notice how my radius is perpendicular to the axis we're rotating around, and that we're rotating around the y-axis and we're in terms of y. That's what drives the disk method. So we're going to say volume equals the integral from a to b pi r squared dr. I know I moved that pi in and out. I apologize for that. So volume is the integral. We talked about the bounds being from 0 to 8. You have to use everything you're given. Pi times, and r is y to the 1/3 squared, and we're with respect to y. I'm going to pull this pi out. The integral from 0 to 8. What is y to the 1/3 squared? Well, you multiply exponents. 1/3 times 2 over 1 is 2 over 3. So we have y to the 2 over 3 dy. I'm going to bring down my pi. When I add 1 to 2 over 3, I get 5 over 3. Take a minute and check that if you're not sure about it, but it's right. 2 plus 1 is 5 over 3, and this will be 3/5 from 0 to 8. So then I have pi. I'm going to put my 3/5 out here. And then I have 8 to the 5/3 minus 0 to the 5/3. Now 8 to the 5/3 is nice because the cube root of 8 is 2 to the 5th power is 32. So when I multiply all of that and subtract, I get 96 pi over 5. 96 pi over 5. Okay. Remember that when you do math, you should pause the video, work through it with me, and then come back and check it, or at least pause and be writing it, taking notes like you would in a math class. The directions on this one say set up but do not integrate. Set up but do not evaluate. When they say that, you should listen. It's there on purpose. often it's impossible. So this says given y equals ln of x, y equals 0, x equals 3 about the x-axis. For the disk method, I would like to make a note here, a really big note. For the disk method, you need to be in terms of the axis you're rotating around. I'm going to add to that soon, but for now, you need to be in terms of the axis you're rotating around. You should make that a big note somewhere. That is a big concept. Okay, so y equals ln of x. Y equals ln of x looks about like this. So that's our first function. Y equals 0 is our second function. It runs right across here, y equals 0. That red and yellow don't look good together. And x equals 3. X equals 3 is a vertical line. Remember, we're in terms of x, and we're rotating about the y-axis. I'm going to throw that over here. So we're going to be the disk method because we're in terms of the x-axis. We're in terms of x and going around the x-axis. And that's pi r squared. So this is the part you're looking at. Do you see that that's touching all three colors? So that's how you figure out which part you're working with and which part you're rotating. So I'm going to let this be my radius because it's perpendicular to the x-axis we're rotating around. So our radius then is natural log of x. And our bounds here are 3, and we know we cross this axis at 1. And the red line helps us cut it off at the x-axis. So we would say the volume equals the integral from 1 to 3 pi, and our function is ln of x quantity squared with respect to x. Yeah, you can't integrate that. That's why it says sit up and do not integrate. Let's look at another one. So this is a new concept because it says the region the region R enclosed by the curves y equals x squared is rotated about the x-axis. Find the volume of the resulting solid. So what has changed here is that we have y equals x, which is a line, and y equals x squared, which is a curve. And so we now have two functions that we're looking at as we look at our volume. So we need to make a note here. Maybe we'll come above this and say, whenever you have two volumes, we're going to subtract the volumes. So we're going to say that the volume equals the integral of pi r1 squared dr minus the integral of pi r2 squared dr. Now this is the outer radius. So it's the longer radius, and this is the inner radius, so it's the shorter radius. When you're working in terms of x, you're going to go top to bottom, top minus bottom. And when you're working in terms of y, you're going to say right minus left. So if you're somebody who memorizes things, you want to catch that. You can say the volume equals the integral pi r1 squared minus r2 squared dr. But I find that students put that r squared in weird places, not in there. So I'm a fan of setting it up into this long one and then combining them when they have matching bounds. Okay, so let's put that into practice here. Here I have two volumes. So I have a longer radius and a shorter radius. Do you see that happening? So we're going to do top minus bottom. This is going to be our R1, and this one will be our R2. I'm ahead of myself, though. We don't have any bounds. The bounds here are 0 to something. The 0 is obvious to see. You can read your calculator, you can know math, or you can do algebra. So let's find our point of intersection first. The easy way to find the point of intersection is to set them equal to each other like we did in the last section. So I'm going to say 0 equals x squared minus x. Factor out that x minus 1. So not 0, but x equals 0 and 1. So my other bound over here is 1. And I think you can see that we're taking this area and we're rotating it around the axis. We're going to rotate it it says around the x-axis. So we want to be in terms of x. That is the disk method, pi r squared. Okay, so let's talk about our first radius. Radius 1, this is our longer radius. See how this piece is longer than the other piece? So our radius 1 is going to be x, and our radius 2 is going to be x squared. So then we're going to say the volume is equal to, I'm going to write it in two different integrals. 0 to 1, pi times x squared dx, because that was our x squared, minus the integral from 0 to 1. When we subtract the volumes, it subtracts out the area underneath the blue curve, just like it did in the area between curves. So it's important to pay attention to that. All right, so then we have the second one is pi, and then our radius is x squared dx. Now, because everything about this matches, we can say they both are bounded from 0 to 1, and they both have a pi, so we have x squared minus x to the fourth dx. Don't worry about the fact that we're in ascending order instead of descending order, that's fine. So let's go ahead and integrate. So we have pi, when we integrate x squared, we get 1/3 x to the third. When we integrate x to the fourth, we get 1/5 x to the fifth from 0 to 1. So we have pi, we have 1/3, I'm gonna put a bracket here. 1/3, I guess I don't need it, minus 1 to the 1/5 is 1/5. I'm sorry, 1 to the fifth is 1 times 1/5 is 1/5. And then minus 0 plus 0. Double check that you end up with a 0 in all those places, okay? So now I'm going to do pi parentheses, common denominator is 15. So the top of the first one is going to be 5, the numerator of the second one will be 3. So we end up with 2/15 pi. And that is our volume when we rotate that crazy. It's kind of like a vase. It kind of has this shape here. So it does the same underneath. So it kind of is a vase look that's open in between the two. Let me pull that picture in for you to see. That gives you a better idea of what that looks like. So kind of makes a little more sense. Okay. All right, let's look at another one. This problem is from the exercises, and it says find the volume when x equals 2 minus y squared and x equals y to the fourth, and we're going about the y-axis. Notice that your equations say x equals and you're in terms of y, so that's a good thing because we're disk method. Okay, so let's pause and think about this. Let's start with y to the fourth. Y to the fourth is easy. Y squared is a sideways parabola like this. So y to the fourth is a sideways parabola. It's just taller and skinnier, and I didn't draw it as such, but we're going to pretend I did. And then we have 2 minus y squared. This minus y squared flips the parabola backwards. Um, Normally, y equals x squared opens up and the negative x squared opens down. So the rules are the same. And then you have a 2. That means this graph shifts 2 to the right on the x-axis. So it's a normal y squared, so it's a little wider than the one we had there. And so we have this equation. It says x equals 2 minus y squared. And my yellow equation says x equals y to the fourth. Now we're rotating around the y-axis, and we're in terms of y, so that makes it the disk method. See it happening there, which is pi r squared. So we're going to say volume equals. Now I'm integrating this stuff. That's what I'm looking for. So I need a long radius to the y-axis and a short radius to the y-axis. Do you see how that works? I have a longer one and a shorter one, and the longer one will be R1 and the shorter one will be R2. And if you do that wrong, then that means that you're going to have a negative volume and you did it backwards. So R1 is the blue one, which is 2 minus y squared, and R2 is the yellow one, which is y to the fourth. So I'm going to say the integral from something to something. Oh, it's labeled. Here I have a 2, and I know this is 0. So the integral from 0 to 2. Wait, that's what we want to write, but that is not correct. Notice that we are in terms of y. Do you see that we're in terms of y? That 0 and 2 are in terms of x. What I need are these red points here, these points of intersection. So let's pause and do points of intersection. And I'm going to set them equal to each other. And I'm going to say y to the fourth equals 2 minus y squared. So y to the fourth. And I'm going to bring them over. Plus y squared minus 2 equals 0. So this factors into y squared plus 2. And y squared minus 1 equals 0. So y squared equals -2. Imaginary, not helpful. Y squared equals 1, so y equals plus minus 1. So those are our bounds. Here we have a bound at -1, and here we have a bound at +1. That makes perfect sense when we're working in terms of y. So let's try this again. Let's say volume equals the integral from -1 to 1, pi, and my longer radius, my radius 1 is 2 minus y squared with respect to y, minus the integral from -1 to pi, -1 to 1, pi, parentheses, y to the fourth squared dy. Does that make sense? We're tempted by this 2 and this 0, but they're x values. Do not pick them up. They're x values, and we're in terms of y. So now I'm going to say volume is pi, the integral from -1 to 1. Now this 2 minus y squared is a binomial, so you need to write it twice and do FOIL, and then you'll end up with 4 minus 4y squared plus y to the fourth. And then I'm going to go ahead and say minus y to the eighth. That's y to the fourth squared with respect to y. So we have pi. We can go ahead and integrate 4y minus 4/3 y to the third plus 1/5 y to the fifth minus 1/9 y to the ninth from -1 to 1. Now there are people who don't want to evaluate both and it's symmetrical. So you could go, your bounds could go from 0 to 1 and then double it at the end. But that always made me a tad bit nervous, so I just didn't do it much as a student, and I don't do it much now. So when we plug in 1, we have 4 minus 4/3 plus 1/5 minus 1/9. Minus, when you plug in -1, you have minus 4 plus 4/3 minus 1/5 plus 1/9. So you can see why you could double it, because we have 4 plus 4 is 8, and minus 4/3 and minus 4/3 is minus 8/3. And we have plus 2/5 and minus 2/9. So when we plug that in our calculator and work it out, or do it on hand, I don't care which way, 248 over 45 pi. Normally I would show you all of that work, but I think you can do it without me. I think you can use your calculator to make it happen. I think you can use your head to find common denominators. It's all good. Whatever you do, just as long as you do it well. I will make one request. Don't give me a decimal. Don't say 5.51 pi. I'm sorry. Don't give me a decimal times pi. So either give me a decimal or a fraction with pi. Don't mix and match. So don't say 5.51 pi. If you're going to say 5.51 repeating, multiply it times pi to give me your decimal answer. Okay? All right. So the second part of this lesson is that we don't always rotate around the axis. Part of this lesson, we don't always rotate around an axis. We sometimes rotate around a line. So what we're going to do is we're going to take, this one is, it says set up but do not integrate. It says y equals sine x, y equals 0. Remember, if it says do not integrate, there is a reason. X is between 0 and pi. That's my favorite way to say that, by the way. And it's about the line y equals -2. So when we talk about rotating around an outside line, let me pull this down and make some notes. Note, we're in the disk method because we rotate around an axis. Around the axis we're in terms of. Or we're rotating around a line parallel to that axis. Parallel to the axis we're in terms of. Parallel to the axis we're in terms of. So that means y equals -2 is a horizontal line and it's parallel to the x-axis. So we would be in terms of x, because if this is our x-axis, this is y equals some negative number. In this case, it's -2. So if we're parallel to the x-axis, we're going to be in terms of x. And if we're parallel to the y-axis, we're going to be in terms of y. So if we have the y-axis here and x equals some number, then this will be, we're in terms of y, because we are either the y-axis or parallel to the y-axis. Hopefully that makes sense, because this right here is the big concept. This is what you have to catch in this lesson, is that we're rotating around the axis we're in terms of or parallel to that axis. So let's look at this, y equals sine x. Y equals sine x is a curve that looks like this, and we are bounded by y equals sine x. That's this first one. Y equals 0. I don't know about you, but I always have to think about that. Y equals 0 is the x-axis. So we're cutting it off here. And we're bounded from 0 to pi. Now, notice it's y equals y equals y equals. That's a big hint that we want to be in terms of x, because in terms of x means y equals a function in terms of x. But we're not rotating around that axis. So let's not put that here. We are rotating around the line y equals -2, which is down here. And this is what makes life a little bit harder. So we're rotating around this line down here, but we're parallel to the x-axis. So we're in terms of x. This is our disk method with pi r squared. Now here's what changed. Here's the big thing. Watch carefully. This used to be my radius because I was going around the x-axis, but I am not. I'm going around this axis here. So if you look at this whole line right here, this part right here is sine x, and this part right here has a 2. So this radius is sine x plus 2. We have to add the 2 to get all the way down there. But notice if we were to integrate that, it's going to integrate all the way down there. Do you see this happening? So we need to subtract out this mess. So this radius, right, this has a second radius here. So this radius is going to be 2. It has a length of 2, no more, no less. It's technically 0 plus 2, but 0 plus 2 is 2. So we can say the volume is the integral from 0 to pi. We kind of lost that in there. We have pi. Our first radius is sine of x plus 2, quantity squared with respect to x. And then we have 0 to pi. Our second radius is 2 squared with respect to x. So to set this up and not continue, we would say, I'm going to put my pi out front. The bounds are 0 to pi. We would go ahead and multiply that out. So we're going to say sine squared x plus 4 sine x plus 4 minus 4 with respect to x. The minus 4 came from the 2 squared there. And remember that when you square a binomial, you do FOIL. And that we can do, but we're not doing it in this lesson, so we are thankful for that. All right, let's look at another one. One says find the volume obtained by rotating the region that is y equals x squared and y equals x about the line what x equals -1. So let's go back to this y equals x squared and y equals x. Y equals x is a line that looks like this. You'll find we use a lot of these over and over. This is y equals x squared. I drew it exaggerated because I wanted to be able to see between them. And we're going around the line x equals -1. So the line x equals -1 is a vertical line over here, drawn to scale way over here. So I often draw my rotating around lines to be dotted. So we're going this way. Now notice we're parallel to y, so we're going to be in terms of y because this is the disk method. And we're using pi r squared. So here we're going to have a long radius and a short radius. The best way to think about that is to pick an area like this area right here. And here you can see that the blue one is farther out than the green one, and that happens almost all the way along, if you can see it here. So the blue one is going to be our outer radius as we head towards the um, or line of rotation. So this blue one's going to be my long radius. That's not a very good color to see. This blue one's going to be my long radius. We're going to call this radius 1. And the green one's going to be our short radius, radius 2. You can see it very exaggerated right here, the way I drew it. Now, my problem with this is right here, we need to pause because we need to be in terms of y. So x equals y is good. But here we want to say x equals the square root of y. So we need the square root of y. Now, when we think about our first radius, I'm going to draw yellow on top of it so you can see, but this first radius length from the blue line to the axis is the square root of y. And then from the axis to the yellow dotted line is 1. So to get all the way from the blue line all the way over to this dotted line, our radius is going to be the square root of y plus 1. Now, when we look at the green line, our length from the green line to the axis is going to be y. And the length from the axis to the dotted line is also 1. So we add them together to be y plus 1. We don't always add. I'll give you a different example or show you a concept in a minute. We found earlier this point is 1, 1, and this point right here is 0, 0. So as we set up our integral, we're going to say the volume equals pi, the integral from 0 to 1 in terms of y from over here. Good news, the x matches, so if you mix them up, you're okay. Our outer radius is the square root of y plus 1, quantity squared, with respect to y, minus pi, the integral from 0 to 1. The inner radius is y plus 1, quantity squared, with respect to y. So then we can say the volume equals pi, the integral from 0 to 1. When I do FOIL, I get y plus 2 square root of y plus 1 minus y squared plus 2y plus 1 dy. So I would like to combine like terms, rearrange a little bit. 0 to 1. Let's start with 2 square root of y. Let's start with the smallest. I hate to start with the negative. It's the only one there. Oh, the ones cancel. I thought that, but I didn't say it. So 2 square root of y, let's move up from there. So I have the y right here, minus 2y makes minus 1y. And then we have remaining a minus y squared with respect to y. So now we can integrate and evaluate. So we get pi. Before I integrate, I would like to write this one more time, just in case. So this is 2y to the 1/2 minus y squared dy. You can't integrate the square root. It doesn't work. So when I integrate y to the 1/2, I get y to the 3/2. Flip that to be 2/3 times 2 is 4/3 minus 1/2 y squared minus 1/3 y to the third from 0 to 1. So then we have pi. When I evaluate at 1, I get 4/3 minus 1/2 minus 1/3 minus 0 plus 0 plus 0. Life is good. So we have 4/3 minus 1/2 minus 1/3. I can do that separately and come up with pi over 2 to be our final answer. So it's a nice and pretty problem. But the important thing is rotating around that outside line. So I would like to tell you that sometimes, let's say we have the square root of x, y equals the square root of x. This could be dangerous because I don't think this problem is anywhere. We're going to go from 0 to 1 on their x-axis. I'm using yellow. I'm not even a big fan of yellow. Oh well. We're going to rotate around this line out here. Let's call this x equals 2. So we're going around the line parallel to y, so we want to be in terms of y. This method, pi r squared. So this point right here is 1, 1. That works out for us when we're working about bounds, and that point is 0, 0. Let's talk about our radius. Remember, your radius has to be perpendicular to the line you're rotating around. So this is one of our lines. I made this problem up because I wanted to talk about this radius. And they show up randomly, but not in a good way to find. And this is our other radius. Can you see that this is R1 and this is R2? So the problem said y equals the square root. You're bounded by y equals the square root of x by y equals 0, which is the x-axis, and by x equals 1. And you're going about the line x equals 2. Yeah, I drew it and then we built it. It's crazy. Okay, so I want you to look at the fact that this one works differently. You don't, when you integrate the square root of x, but we're going to be in terms of y. So let's call this x equals y squared. Are you with me on that? Now notice the second line right here. Let's put it in red. This is our second line right here, and this is the line x equals 1. So we do have two functions here in terms of y. It's not a function in terms of x, it's a function in terms of y. Now when you integrate this yellow line, I'm going to pick a different color. When you integrate this yellow line, you're really finding this area right here, the area between the yellow line and the curve. Like I can't color it all in because it won't get to stay, but you're really finding this area right here. So the problem is you need the radius, you need this green line going from this yellow dot, you need this radius here. You need the green line going from the dotted yellow line to the solid yellow line. But when you integrate, you get this white line here. So remember, I'm going to try to find another color. My problem is I'm running out of colors in this problem. I used too many colors. I don't think I've used this blue yet. This line right here is 2. It has a length of 2 because this is x equals 2. So when I integrate with respect to y the value of 2, it gives me all the area between the dotted line and that line. And I want to subtract out this white piece. So I'm going to say 2 minus the function. So I get 2 minus, in this case, the function is y squared. By the way, notice it's the top of a half of a parabola, so that makes sense. And then on the bottom one, this whole line right here, the length is 2. Again, this length is 2, but I want to subtract out all of this squiggle, which is the length of 1. So we're going to say 2 minus, in this case, the function is 1. So 2 minus 1 is 1. So I'm going to summarize this for you on the next section. Let's just keep going. The volume then is pi, the integral from 0 to 1 in terms of y. So my first radius is 2 minus y squared squared. And I'm going to subtract pi, the integral from 0 to 1. And my radius here is 1 squared with respect to y. So we're going to say pi, integral from 0 to 1. Remember to do FOIL. So we have 4 minus 4y squared plus y to the fourth minus the 1 at the end dy. So we have pi, the integral from 0 to 1. Some people integrate that like it is. I like to combine like terms as much as possible. So 4 minus 1 is 3 minus 4y squared plus y to the fourth dy. Now when I integrate, we get 3y minus 4/3 y to the third plus 1/5 y to the fifth from 0 to 1. So we have 3 minus 4/3 plus 1/5. When I plug in 0, I get all zeros. So we get 28 over 15 times pi. I would like to summarize this for you. So our disk method has some important qualities around it. It finds the volume for us. We want to be in terms of the axis we're going around, in terms of the rotation of the axis of rotation. Let's write it that way. Or parallel to the term parallel to that axis. Can we just say it that way? Have we done enough to say it that way? Underneath here, let's say plus or minus an outside line of rotation. So if you're going around a line parallel to y, you're going to say you're in terms of y, and your radius is either going to add or subtract. So there's kind of, this is not a really good explanation, but if your rotation line is this way, you're going to add, and if your rotation line is this way, then you're going to have to subtract. And you can think about that in terms of x as well. And I'd like to make the notation that we're using pi r squared. And then we also use, let's say, the integral of pi r squared dr. And then we have the integral of pi r squared, the pi parentheses r1 squared minus r2 squared with respect to r. So that kind of summarizes 6.2 for you on this screen, and I hope it makes sense. If not, set up a time to meet with me and let's work it out. Have a great day.